Okay, well, so here we are. It's eighth week, and on Friday we did an application of the Metropolis algorithm for deciphering deciphering a message, right? A coded message, and I thought that was kind of cool. I've already posted homework five. Homework five, I'm hoping, is easier and lighter weight. Yeah, I mean it's coding, and so if you hate coding, then you're not going to enjoy the entire 102 series. There's only three questions, and one is just play around with the deciphering code. Okay, so I've posted that online. You're gonna play around with it. There's like some coded messages there, and you just decipher it. And I hope it's at least kind of fun to see it run on your computer. And then the other part is you run two Markov chain Monte Carlo algorithms for multivariate MCMC. Okay, and so I want to talk about that today. Okay, so big picture of the course is we do Monte Carlo methods to avoid tough math, right? We try to get estimates of our answers by drawing from random distributions, and then we can apply functions to these random distributions or random values and get estimates of whatever it is that we're looking for. Okay, so we did things like Monte Carlo integration, Monte Carlo estimation, and then we spent a lot of time just talking about how to generate random values from some distribution. Okay, and all of this Metropolis algorithm MCMC stuff was just to say, here's another way to get random values from some target distribution. And there were nice properties of MCMC in that, or at least for the Metropolis algorithm, you only needed something that was proportional to the target distribution. You don't even actually need to know the exact form of the target distribution, which is very handy for us. And today we are going to kind of expand and delve into a multivariate application. Okay, so even that deciphering algorithm, as complex as it was, there was only one unknown parameter, which was just the mapping of letters. Okay, and that was only one, and we proposed one, and we either accepted it or not. Okay, so far our MCMC methods which is the basically Metropolis and Metropolis Hastings algorithms, have been univariate. Okay, and so but a lot of times we might have a multivariate distribution. Okay, okay, and so I guess today we'll just start off with the multivariate generalization of the Metropolis and Metropolis Hastings algorithms. Okay, and we'll start there, and then I'll kind of discuss some issues that we encounter when we have a multivariate Metropolis or Metropolis Hastings algorithms. Okay, but so we'll just keep it simple, okay? So let's say, so we'll start off with a kind of simple example. Okay, so let's say our target distribution is a bivariate normal distribution. Now we've already it's kind of silly to run MCMC on this because we already know how to generate values from a bivariate normal, right? We did the transform from two independent normals into a bivariate normal, and that was learned you learned that for the first midterm, but just for illustration, we're going to have this, okay? So let's say our target distribution is a bivariate normal distribution, so we've got our vector x comes from a normal distribution with a mean vector mu and variance covariance matrix sigma, right? And maybe if we make a contour plot, maybe it looks like this. Is there a way to okay, I don't know how to do this. Never mind. Okay, I'll just draw it. Okay, so let's say we've got a multivariate normal distribution, and it looks something like this. Okay, so this is kind of our contour plot for x1 and x2. Okay, and so this is you've got some PDF here, right? So the PDF, and I gotta look this up. Multivariate normal distribution. We'll go to Wikipedia. Okay. And this is our PDF. It's 1 over root 2 pi sigma. It's basically so 1 over the determinant of 2 pi sigma to the 1/2. So it's basically like the PDF of the normal, but it's 1 over root 2 pi sigma, and then exp of 1/2 x minus mu transpose sigma inverse x minus mu. Okay. Negative 1/2 x minus mu transpose sigma inverse x minus mu. All right, so that's our PDF. Okay, I'll just tell you, the Metropolis algorithm and the Metropolis-Hastings algorithm work almost exactly. Well, I don't know. I think it makes sense to me, but of course I would. It works exactly as you might expect it to work, okay? So you would start off with some kind of starting location, all right? So let's say this is our x at time 0. Where do I write this? Okay, so I'll write x at time 0. All right, maybe I'll just put it down here. Okay, so this is our vector at time 0. So this is our Metropolis algorithm. Okay, so we'll start with x at time 0, which is going to be, I guess, x1 and x2. I don't know how to subscript this. x1-0, x2-0, whatever. Okay. some funny notation. All right, so you just start here, right? And then you have a proposal distribution. Okay, that depends on your current value, x0, okay? And so it could be anything. Probably a good choice is like a normal distribution, bivariate normal distribution. So your proposal distribution has to be of the same, of the same dimension, right, as target. So in our case, our target distribution is two-dimensional, so our proposal distribution has to be two-dimensional, okay? So our target is two-dimensional, so our proposal will be two-dimensional. Okay, all right. What were some proposal distributions that we had for the Metropolis algorithm univariate case? Continuous. We had the normal distribution, and then what was the other one? Uniform, right? And likewise, we can have the same, you can have any proposal distribution, but I would say probably most common choice is the 2D normal distribution, okay, with your sigma matrix equal to, something times the identity matrix, meaning there's no covariance, right? Okay, and so what does a normal distribution, bivariate normal distribution with no covariance look like if we drew contour lines? It looks like concentric circles, right? Centered at, so we would have, you'd have a circle. So this is your proposal distribution. And then just from here, you just generate some random proposal, okay? So if I just kind of scroll up here, so let me just kind of copy this down. I'll come over here. So this is what I have, and okay, so we would propose a, okay, so we might propose this is our new value that we propose, okay? So this x star, this is our proposed value. Okay? Or another choice. Another choice for the proposal would be some, you could have a uniform distribution. Centered at x0, okay? And uniform would be like this. And here, if this is x1 at time 0 and here's x2 at time 0, it would be uniform. This corner would be x1 at time 0 plus 1 and x2 at time 0 minus 1. and then, x1 at time 0 plus 1, and x2 at time 0 plus 1, right? And you can kind of define the four corners of your square and just say, we're going to pick a random location on this square with uniform probability. So maybe we pick right there. Does that kind of make sense? So just uniform distribution centered at x0, and pick a random location in the region, okay, for your proposed value. Okay, so far so good. This is your target distribution. You have a proposal distribution centered at x0, and you get an x star. So now that you have x star, now that you have a proposed value, okay, what do? We will calculate. What do you think we'll calculate? You guys are breaking my heart. We'll calculate p move, and this will be equal to the minimum between 1 and p of x star divided by p of x current. Okay, so it's exactly the same as before, right? It's just p of x star, you now have to use this two-dimensional PDF, okay? So now you have a two-dimensional PDF. So the function for p of x star and p of x current the function is two-dimensional, but the probability value it spits out is just one value, right? It's a probability value. It's going to be, or it's a probability density, okay? So it's just a single value. So you plug in your two-dimensional location x star, okay? I guess I should indicate that x star is a vector, okay? So you generate a proposed value, and you plug in x star versus x current, all right? And then you move with probability p move. Okay, and so basically just draw a U and move if U is less than p move. Okay, and then if you move, the next x value is equal to the proposed value, and if you do not move, the next x value is equal to x current. And so I hope this feels kind of like a natural next step, okay? And it's just, instead of having a univariate proposal distribution, now you have a multivariate proposal distribution, okay? And probably the most common choice is a multivariate normal, right? Which means we're generally going to propose values within kind of our circle, a smaller radius to our current location, but we might propose a value that's a little bit farther away, okay? But yeah, you can also propose uniform and things like that. And if your target distribution is three-dimensional, then you've got a three-dimensional target distribution, and you'll have a three-dimensional proposal. And now you'll be proposing values in a multivariate, multi-normal, I guess a multivariate normal distribution, which will look like a sphere, like if they're all independent. So you'll have like concentric spheres or something, or some kind of cube if it's uniform, where there's equal density within there. Okay, and you can go into higher dimensions, and it's just the same. Okay, so can we all visualize what happens in higher dimensions here? At least, you know, however your brain represents higher dimensions than 3 dimensions. And so that's what we have. Okay, and this works in the long run. In the long run, the multivariate Metropolis algorithm works. Okay, if we did not have a symmetric distribution for the proposal, right? If it weren't concentric circles like this normal multivariate normal or this square, okay? So if it wasn't a symmetric shape, then you'd have multivariate Metropolis Hastings, and you'd need to include the kind of the term that adjusts for the difference in proposal probabilities, okay? Do I need to write that down, or you guys got it in your head? Okay, so that works. Okay, there's an issue though when we do this. Okay, and the issue is at higher dimensions, it's harder to hit our target. Okay, so yeah. Okay. So I guess this is our curse of dimensionality. Right. In higher dimensions, it is harder to hit our target. Okay. I should say hit our target with the proposal distribution. Okay, so let me just kind of contrast this. So if you have univariate, right? Let's say this is our target. Okay, and this is X current. All right, so as far as proposal goes, let's say you used this is your proposal distribution. And basically, if you propose anything this way, you're going to accept it, okay? Because if we imagine this being very flat, like anything this way has a higher probability. I know I drew it flat, but this is, just imagine like the normal distribution where it's almost flat, but it's not exactly flat. So anything this way will be accepted. And then this side going this way is less likely to be accepted, right? So the kind of the lower bound for acceptance out at here is 50%. Does that make sense? So the lower bound for being accepted here is 50%, because we have a 50% probability of proposing a value that has a higher probability than what we've got, and then we have a 50% probability of proposing something with a worse probability, which we still sometimes accept according to the Metropolis algorithm, but we're less likely to accept them. Okay, that's the univariate case. All right, let's look at the multivariate case. Okay, so we'll do a bivariate. Okay, and so here's our So we're here. So this is our target, okay? And let's say this is where we start off, x0, okay? And our proposal distribution looks like this, okay? So the best area is down here. And so if we look at this, as far as proposed values go, these values here will for sure be accepted. Except for sure, right? Because we're getting closer to these values all have higher probabilities in the target PDF than our center, okay? And these ones are less likely, okay? These ones definitely, except for sure, because they have higher probabilities. These ones have lower probabilities, so they might be accepted. So maybe accepted. And then, you know, these regions out here, okay, here and here, these are like of similar probability levels, okay, if we think about. So this is, you know, maybe accepted, maybe not. They're kind of, it all depends, like, we have to kind of draw, like, how big this larger contour gets drawn and stuff, okay? So we're not quite sure. So kind of the lower bound for the acceptance here is now 25%, okay? Does that kind of make sense, what I'm trying to say, the lower bound for acceptance? Okay, because we can say, like, we got a 50% probability of proposing something closer in the x1 direction and a 50% probability of proposing something closer in the x2 direction. Okay, but then we might propose something good or bad in the other directions, and it's harder. And we can imagine, just as we scale up in the number of dimensions, okay, like let's say we were in a situation where the drop off in the things are harder. So let's say, you know, would say 17 dimensions. Okay. It is hard to propose a value that will kind of for sure be accepted, right? Before we could just look and say, like, is it closer or no? Because now there's 17 independent, kind of, not necessarily independent, but 17 values, and maybe 16 of them, by some miracle, could be of a higher probability. But if that 17th value has a very low probability, like for whatever the proposal distribution just generated, you know, the 17th value to be very unlikely, then this value will likely be rejected, okay? Has a low probability, then, you know, the new location in 17 dimensions, you know, might not be accepted. Okay. So as we get, you know, if we're just thinking about how our proposal distribution works, okay, it just kind of proposes indiscriminately, and in high dimensions, we might propose something. It might be difficult to propose something that seems like it's a number that we should accept. Okay. So for example, if we wanted to just I don't know if you ever play video games and you you have like character customization, right? And they might have like 20 different traits that you can customize about this character that you're creating, right? You can customize their hair and their skin and their clothes and whatever. And oftentimes there's like a random button, right? And you just click random, right? And so now you have to think like, you might say like, oh, I'm open to whatever my character looks like. But then when you click random, and it just randomly picks all of these values all at once, usually the combo of all of those things is going to end up being terrible, right? It's like rarely do you get a combo of all 20 things and you're like, oh yeah, I like that. You might say like, okay, I like 6 of these things that this random generator picked, but these other things are terrible, okay? And if you had said, well, am I going to accept this custom character just based on this completely random thing, we're going to say no, okay? And you can just keep hitting random and random and random, but because the computer is just randomly picking all of these 20 traits independently, it never produces a character that you like the look of, okay? And so instead, a better approach would be to maybe you can just pick one of the values, one aspect, and just randomize one of them and say, oh, man, this looks good or something, okay? And if you're able to just randomly pick one at a time, then you're probably more likely to get something that you like rather than something so crazy, okay? I don't know if that makes any sense. It's a video game reference that maybe 5 of you appreciate, but that's okay. The idea is when we're using a high-dimensional proposal, we run into issues, okay? And in your homework this week, you barely see it, okay? Because I only have you guys visualize it for 2 dimensions. But this becomes an issue in higher dimensions, okay? And so eventually, okay, so maybe at the next, I think next week. Oh, so by the way, we are having class on Wednesday. I'll be here. Maybe you won't be here, but I'll be here, okay? And I will cover lecture stuff, and you are responsible for that thing that I cover, okay? Next week, we're going to talk about the Gibbs sampler, which kind of breaks down a multivariate thing into a bunch of individual ones, okay? And then, but before we get there, I want to kind of talk about the hierarchical model in Bayesian statistics, and because that's kind of the central I don't know about the central, but a primary application of the Gibbs sampler. Okay, but so next week we will talk about the Gibbs sampler, and this is a way to kind of break apart a very multidimensional distribution into a series of univariate distributions. Okay, and it's all kind of conditional. And this improves our our acceptance rates. Okay. All right. I kind of hate to do this, but I'm going to do it, and I'm going to verify the attendance poll, and so we'll take our last bit of class time and do that.